rest. We also have PCO2. We'll do the same diagram. So we have our lungs, we have our tissue, and the various capillaries associated with that. Remember, the partial pressure of CO2 at sea level is 0.3, so it's 0.04% or 0.0004 times 760 is 0.3. As you inhale, that is the opposite, so it gets concentrated to 40. Because of Henry's law, it comes out of the pulmonary capillaries at 40. It does have a venous admixture, but it's not enough to worry about, so we keep it at 40. In the tissue, because of metabolism, the CO2 is 45. When blood comes in at 40, the tissue's at 45. That gives us a gradient into the blood. Because of Henry's law, it comes out at 45. It goes into the pulmonary capillaries at 45. Because of that gradient, it moves into the alveoli. So remember, gas moves because of partial pressure gradient. So at sea level and rest, the magic numbers for CO2 were 45 and 40. Again, the point I tried to make the other day when we talked about this is oxygen needs to come from the atmosphere into your cells to be used. You need a partial pressure gradient to do that, so it must step down at some point in time in order to have that gradient, right? In terms of CO2, it has to be the opposite. We're making it the tissue, it has to step down the opposite way, highest in the tissue, lowest outside. So if you go, okay, I remember 40 and 45, oh, it has to be highest in the tissue has to be 45. And then you remember Henry's law, it has to come out at 45. And then remember there's no exchange in the veins, and it goes into the pulmonary capillaries at 45. It's a good start in terms of remembering what happens. You know, the other two things we talked about was exercise. Remember we said exercise because of hyperpnea, because of the increased breathing. The arterial side and the alveoli match. So we increase breathing to keep our 105 and 40. But the tissue, because of the increased metabolism, the oxygen gets lower in the tissue because we're using more oxygen up, so there's not as much around. And because we're using more oxygen, the CO2 goes up because we're producing more CO2 in metabolism. Again, we said you can't really come up with a number. It has to be less if it's exercise than the two numbers we have here. But it depends on the level of exercise, right? I mean, if you walk up the hill to class, you know, your oxygen might go down to 38. You know, it's not really very, and your CO2 might go to 46 or something. You know, if you exercise really hard, it might go to, you know, 10 and 50. All right? And if you did that, then it would be, you know, 10 in the tissues, 10 coming out of the tissues, 10 going in the lungs, right? And the same thing with 50. And then we looked at altitude and rest. And so with altitude, because your metabolism was the same, the stuff coming in was different, but the tissue stuff and the other side was the same. And as we said, it depended on the level of altitude, and there was really no formula to predict this type of stuff. But let's say you're 18,000 feet where the barometric pressure was half of what it is here, then we said not a bad estimate is, you know, the partial pressure of oxygen in the ambient air would be half of 159, 79 and a half. And that would make, you know, studies show about 60 in your lungs and then 60 coming out and so on. And that's the reason why we said it's harder to breathe at altitude is you have less pressure gradient, right? So your tissue's still 40, but the blood coming into the tissue is only 60. There's less gradient, you can move less oxygen, and it's harder to breathe. Okay? And then take an extreme example. We didn't do these numbers, but we kind of talked about it in other terms. You know, if you're flying in a plane at 40,000 feet, and for some reason the cabin depressurized, right? Then the partial pressure of oxygen at 40,000 feet is probably 25, which means the gradient is actually out of your body. And we said, you know, that's not going to tell you to put those oxygen masks on quickly and first before you do anything else, because as soon as you do that, you're literally removing oxygen from your body because the partial pressure gradient is no longer into your tissue, but out of your tissue. And, you know, that becomes, you know, very dangerous in terms of, you know, being able to breathe and stuff like that. Right. So that was number one. That was PO2 and PCO2 for the various things. 2 and 3, I grouped the hormones for GFR and regulation of water and really regulation of mean arterial pressure then together. And I grouped them together because they make sense, and we kind of said ADH and antidiuretic hormone and angiotensin 2 do the same things essentially. They have slightly different mechanisms of action, and you know, they both kind of have a primary and secondary role that are reversed, but the bottom line is they're very similar. And so probably not a bad way to look at them, just to look at them together and kind of see how similar they are. I grouped the other two, aldosterone and A and H, together because they are antagonistic hormones. And if you know one, then you know the other one for the most part. I mean, the details are slightly different because it does the opposite. So over here, I'm going to put ADH. We'll talk about those things. And over here, I'm going to put AG2, which is angiotensin 2. We'll kind of look at what they work. So remember, ADH, known as antidiuretic hormone, also vasopressin, VP or AVP for arginine vasopressin. Okay? It's made in the hypothalamus. But then it's transported and released from the posterior pituitary. So it's made in the hypothalamus but released from the posterior pituitary. Angiotensin 2 has that complex, what we call the RAS, the renin-angiotensin activating system. And so we go from what we call proangiotensin, or angiotensinogen, that's the precursor. We said that was made in the liver, and it floated around the bloodstream. We said renin converted proangiotensin to angiotensin 1, and then ACE, that angiotensin converting enzyme, converted angiotensin 1 to angiotensin 2. This comes from JG cells, the renin. This happens in the blood, though, conversion to angiotensin 1. ACE is in the lungs, and that's in the capillaries. And so angiotensin 2 really is made in the blood capillaries of the lungs. Okay? So it's kind of complicated where it's made because it's that whole, what we call RAS, renin-angiotensin activating system. So proangiotensin is converted to angiotensin 1 by renin, which comes from JG cells. Proangiotensin is made in the liver. It's a protein. It's not active, though. That's what we call pro. In the blood, we convert proangiotensin to angiotensin 1. We would cleave off a few amino acids. And then in the lung capillaries, where we have ACE, the angiotensin converting enzyme, it converts angiotensin 1 to angiotensin 2. Angiotensin 2, by far the most important one from a biological standpoint, right? It has by far the most activity. What are the actions of ADH? Well, ADH, remember, opens aquaporins, remember the water holes, in the distal convoluted tubule, right? So particularly in the principal cells of the distal convoluted tubule, right? So it opens aquaporins, the distal convoluted tubule, that increases water, or we'll say blood volume, how about that? That's probably a better way to say it. And that increases mean arterial pressure. So its major one is open aquaporins in the principal cells of the distal convoluted tubule. In addition, it's a slight vasoconstrictor. So its secondary action is vasoconstriction, where it causes smooth muscle of arterioles to contract, and that increases TPR, and that increases mean arterial pressure. All right, so that's the mechanism of action. It's got two. The ADH opens aquaporins in the principal cells of the DCT to reabsorb water, and then causes vasoconstriction, which increases TPR, increases mean arterial pressure. Angiotensin II does sort of the same thing. The primary and secondary actions are reversed, slightly different mechanism of action, but first, if I can spell vasoconstriction. So the first, its major action, it's by far the most potent vasoconstrictor we have in the body. So its first mechanism of action is vasoconstriction, which increases TPR and increases mean arterial pressure. So its primary mechanism of action is the exact same as the secondary mechanism of action of ADH. Again, angiotensin II is literally thousands of times more potent than ADH in terms of vasoconstrictive effects. Right? So you need at least 1,000 times more ADH to get the same vasoconstrictive effects of angiotensin II. However, it's also got a secondary effect, and we're going to say vasoconstriction of afferent, right? So your afferent arterial. And if we vasoconstrict the afferent arterial, right, we're going to get kind of the same thing. We're going to decrease GFR, right? Remember, if we vasoconstrict the afferent, that puts less blood into the glomerulus, which decreases the pressure. So we decrease GFR. Since we have less fluid going as ultrafiltrate, we increase blood volume, and we increase mean arterial pressure. So why I say it's different mechanism of action, we constrict the afferent instead of opening aquaporins. It does the same thing ultimately. It increases blood volume, it increases mean arterial pressure. So together, they are very similar in terms of their mechanism of action. In the one, the primary action is the secondary of the other. In the other, they both increase blood volume. One's primary, one's secondary. And they do it in slightly different ways. But the bottom line is they're very similar in terms of what they do in terms of that. Now, some of the things we talked about, we might as well kind of finish the ideas. For ADH, we talked about pain and stress and trauma, right? Increasing ADH, and those things help you to hold on to water. Okay, so, and that's when you need it. When you need more blood pressure, you need to maintain blood volume, things like that. The one thing we talked about reducing ADH was alcohol, right? So alcohol reduces ADH, so you pee more in terms of that. And then we talked about diabetes insipidus, which is actually question number 7. I hopefully we got time to answer it. But remember, diabetes insipidus has to do with a reduction in ADH, or you're not responding to ADH, right? So your glucose isn't affected, but other things are. For angiotensin II, we talked about it's the JG cells that control all this. If JG cells release renin, then you're going to make more angiotensin II. So the rate limiting step is how much renin you release from JG cells. The more renin you release, the more angiotensin II you're ultimately going to have in terms of that. And, that was, the big things we talked about angiotensin II. So it's a nice little comparison of those two hormones. Okay? The other two that we talked about that are on the list for number 3, aldosterone and ANH. So let's kind of finish it up. And again, there's a very nice table on hormones that kind of look at some of the important things here. So we're going to compare aldosterone with ANH. Remember aldosterone, because it ends in "-one". It's a steroid hormone, right? So it's relatively slow acting. And it's one of the 3 water conservation hormones. The first 2, water conservation, increase water, increase mean arterial pressure. We saw that. Aldosterone is going to do the same thing. And then ANH, right, is the water releasing hormone, atrial natriuretic hormone, natriuresis, get rid of sodium, Na, sodium. Right? So aldosterone is made in the adrenal cortex. Okay, it's actually the zona glomerulosa, right? But we don't have to worry about that. So it's made in the adrenal cortex. ANH is made in the atrium. Right? That A stands for atrial. So ANH is made in the atrium. What aldosterone does is it increases the activity of the sodium reabsorbers, or number. So I'm going to put increases activity / number, Na plus reabsorbers. Remember, those are the proteins that reabsorb in ascending limb. So remember, the ascending limb of the loop of Henle is permeable to everything but water. And what happens is we increase the amount of sodium reabsorption in the ascending limb. Now, as we put more sodium into the interstitial space, that creates a greater osmotic gradient, and more water is pulled from adjacent nephrons. So the water doesn't follow it directly, but eventually it does, and so you end up as a net from your body reabsorbing more water. So, here's the bottom line then. We increase the sodium, which leads to an increase in blood volume, because water follows because of the osmotic gradient, which leads to an increase in the arterial pressure. Right, so that was what we did with aldosterone. We increased the sodium reabsorption and water follows. Pretty much. Well, ANH we put here because it's the exact opposite, right? We decrease the activity / number of Na reabsorbers in ascending limb. So we're going to pull less sodium back into the body, which means more sodium is going to stay out in the urine because of its osmotic gradient. So we're going to decrease the sodium, which is going to decrease blood volume, which is going to decrease mean arterial pressure. So again, except for where it's made and what stimulates it, it causes the exact opposite response. So again, easy to remember them together. If you know one, you know most of the other one. And that was the point I was trying to make. You don't have to roll and memorize it all. You know one, you know the other. Now aldosterone, we said because aldosterone increases sodium reabsorption. We saw it stimulated by a couple things. One was low blood volume and pressure because it increases those, and low sodium because it increases that. We also said because of that isoelectric equilibrium we talked about, also high potassium stimulates aldosterone. So if you have excessively high potassium, what you do is you kick on aldosterone, you retain sodium and spit out potassium in its place. Remember, you have to exchange those positive ions or do other things like, co-reabsorb a positive and a negative like bicarbonate or chloride. In terms of ANH, what really seems to be the big thing that triggers it is low blood volume. So you have less pressure in the atria, which causes less stretch, which, has no effect. But, high blood volume. Did I say low? Yeah, so it's high blood volume, right? Because we want to get rid of blood volume, we want to get rid of fluid. So that increases the stretch, and by getting rid of the volume, that decreases everything in the atria, goes back to normal. So high blood volume, high stretch, pressure in the atria is what causes it. And again, it took them a long time to figure out because nobody ever looked. Hey, it's in the heart, because you don't think of the heart as being an endocrine gland. But as soon as they found it, they said, oh, it makes a lot of sense for that reason, right? Because we're going to see those changes in the heart. So it's kind of a quick nutshell, making sure we try to get done with everything for both the set of hormones. And again, if you kind of remember them the way they're presented, they're not too different from each other in terms of that. And that comparison of them in a little chart is very nice.
Angiotensin 2 also stimulates aldosterone?
Yeah, probably. Aldosterone stimulates angiotensin 2, and ANH suppresses all three. So it wouldn't be surprising if one day we found all three of the water conservation hormones stimulate each other in some way, somehow. And some of them actually have a direct effect on the hypothalamus, which stimulates production of ADH as an example. So I'm guessing one day when we figure it all out, they'll all support each other.
About that kind of detail on the test.
Probably not that sort of detail. Anything else with that? All right, so number 4 is getting at the net filtration pressure idea. And we talked about NFP and things like that. Remember we said, one of the first things was net filtration pressure. Is knowing what net filtration pressure is important because NFP directly determines GFR. And one of the points we're trying to make is if GFR is very stable, right, under a high variety of conditions. Like I said, if you don't drink water until tomorrow night, your GFR is going to be the same. If you drink a glass of water every hour until tomorrow night, your GFR is going to be the same. So the ability to regulate it. And GFR is determined by NFP. Since GFR is highly constant, NFP is highly constant, right, in terms of that. Although we don't technically regulate NFP homeostatically, it's essentially is. So one of the points is if NFP goes in half, what's going to happen to GFR? It goes in half. Even though GFR is regulated, it's determined by NFP, so you have to kind of remember that. So NFP is net filtration pressure. And it's what determines GFR. Okay, so again, if it changes, GFR changes. And we can look at NFP and say, okay, NFP is calculated by forces out minus the forces in. The forces out are the glomerular hydrostatic pressure. All right, so the hydrostatic pressure of the glomerulus, the pressure within the glomerular capillary, plus Bowman's capsule oncotic pressure. All right, I always say capsular oncotic pressure, I think is what we called it before. So COP, capsular oncotic pressure. That's the force in, out. The force in is glomerular oncotic pressure plus capsular hydrostatic pressure. All right, so one of the ways to remember, that's why I use capsular, although it's kind of vague. I remember, CHP and COPS are the ones that kind of deal with police. The two capsule ones. And so that's the basic formula. You're given some numbers, and so we're given GHP is 46, VCOP or COP is 0. It's 0 because normally there's no protein in the filtrate, right? So that's what I call ultrafiltrate, so there'll be no protein there, so it's 0. And then we're given 28 plus 7. So if we go 46 minus 35, that gives me a net filtration pressure of positive 11. That means that we favor filtration, which is good because we're trying to have a glomerular filtration rate. It should never be negative in your kidney. That would be bad. All right, so NFP is positive. We said a normal NFP is about 10 to 15 for most people. And somebody in an NFP at 10 might have a normal GFR at 125 mils per minute. And somebody at an NFP of 15 might have a normal GFR of 125 mils per minute. Remember, so that's the number to know for GFR, 125 mils per minute or 180 liters per day. Okay, so those are kind of the two magic numbers in which to look at. A couple other things then that, we kind of look at is, let's kind of look at the different scenarios and see what's going on. So there's given some scenarios in the handout. It says, okay, in A, you've got severe hemorrhaging where blood pressure goes from 93 millimeters of mercury down to 31. Okay. So if we go from 93 to 31, the glomerular hydrostatic pressure is going to drop significantly because arterial blood pressure drops significantly, right? Way below 50. We'll see why that's important in a second. So it drops to 31. And in fact, this drops so low, the GFR probably go down to 0, but significantly decreases. If GHP goes way down, right, everything else stays the same, we're going to have a drop in GFR. So this is going to decrease net filtration pressure, which is going to decrease GFR. All right. In B, we have sort of what appears at first to be a similar situation where we go from what? 106 to 138. And one of the points we made about GFR and NFP as well is there's a regulated range in which we can regulate NFP with drastic changes in blood pressure. And the magic numbers I said to remember were 50 to 150, which means if blood pressure stays within that 50 to 150 range, we can auto-regulate it so NFP doesn't change. Okay? In this first one, we went below 50. We're out of the range, so we can't regulate it anymore. So that means it drops significantly. Here, we're between 106 and 138, right? Which is between 50 and 150. What does that tell us about the ability to regulate it? We're cool, right? So we're good. So what's the change in NFP then? None, right? So there's no change in NFP because of auto-regulation, because we're in the regulated range, and therefore no change in GFR. Does that make sense? Okay. So C was somebody who's malnourished and blood proteins go from 8 to 4. So here's somebody whose blood proteins normally should be 8 grams per deciliter, right? They go down to 4, so they go in half. Which of these is that going to affect? The glomerular oncotic pressure, right? As a matter of fact, you can even go, okay, oncotic pressure, osmotic pressure in this case, that's due to proteins, is solely due to the number of proteins. If you went from 8 grams per deciliter to 4 grams per deciliter, it's not unlikely that your number of proteins went in half. If your number of proteins go in half, what happens to your GOP then? They go in half, right? So if it goes to 14, right, let's say, then that goes 46 minus 21, what's that, 25? So we're going to increase NFP, right? Does that make sense? Because the back number is going to get smaller. Since we increase NFP, we're going to increase GFR. And again, think about it this way. As fluid gets filtered, most of the fluid gets pulled back by the proteins. Remember, think of them as a sponge, sucking fluid back. If there's less proteins, we're going to suck less fluid back, which means more is going to be filtered. Does that make sense? Which is, by definition, an increase in GFR. So C will increase GFR. For D, we destroy the podocytes. So the first thing you have to remember is what do the podocytes do? Well, the podocytes are selective filters, right? So if we destroy our selective filtration, what of interest in this problem is going to change? All right, COP and GOP both, right? Because the ones that end up in the capsule are going to come from where? The glomerulus. And what happens is the podocytes serve as our selective filter. They help to keep protein as well as the formed elements, but in this case protein, out of the filter. If we destroy our podocytes, now protein's going to leak through. And it's a double whammy. So not only does the COP get bigger, because now we have proteins in Bowman's capsule, but where'd they come from? The glomerulus. So the glomerulus, the GOP gets smaller, the COP gets bigger. And that difference just gets greater and greater. Does that make sense? So we have an increase in net filtration pressure because this number is bigger, this number is smaller, that increases NFP. And again, if we increase NFP, we increase GFR. Does that make sense? So those are the things that can happen during that. Number 5, I'm not going to put on the board because it's pretty simple, but I'll explain it fairly quickly. What are the processes that form urine, right? For urine formation. So how do we do it? 3 processes: filtration, reabsorption, secretion. Filtration happens where? Glomerulus. And we form ultrafiltrate, right? which means it's protein and cell-free. Okay, and what gets filtered? Well, that's easy. Everything but protein, red cells, white cells, platelets, right? So, and that's why we call it ultrafiltered because of that. Reabsorption happens primarily where? Proximal convoluted tubule. Remember, first, you want to reabsorb good stuff first. Things we typically reabsorb would be like water, amino acids, glucose, bicarbonate, things we want to keep. Okay? Secretion happens primarily where? DCT, distal convoluted tubule, and things we secrete are often, xenobiotics, other things like waste products, depend on acid-base balance, hydrogen. We mentioned that PAH as an example of things in terms of that. So 3 processes form urine: filtration, reabsorption, secretion, kind of each one. And then the 5 steps in respiration, because that one's simple too. So the 5 phases of respiration, remember ventilation, exchange between air and the lungs, right? That's explained actually by Boyle's law. Pressure is inversely proportional to volume. We increase the volume of our lungs, which decreases the pressure, and air moves in. Vice versa for out. So first one is ventilation. Second one's the hard one, external respiration, right? Because if you open your mouth, you're continuous with the atmosphere, right? So it's what we call external respiration. Exchange of air between the alveoli and the blood. Okay, once we get in the blood, it's gas transport. That's number 3, gas transport, moving gas to various parts in the body. In terms of oxygen, primary movement is from the alveoli, capillaries, so the pulmonary capillaries, to the tissue, and CO2 is going the opposite way. So 4th would be internal respiration, exchange of gas between the systemic capillaries and the tissues. And then the 5th one is cellular respiration, where you're actually using oxygen in metabolism and making CO2. Okay? So CO2 leaves by the exact same process, just reversed, right? So again, just in a nutshell, ventilation, external respiration, gas transport, internal respiration, cellular respiration. Okay? Sounds pretty simple in terms of 5. 6 is talking about clearance. Right, you have to do it in lab as well as lecture. In lecture, you're not going to get the formula. So clearance, remember we said, the way to remember clearance is UV over P. So clearance equals UV over P. And again, U equals urine concentration. V equals urine production rate, and P equals plasma concentration, and basically ask you for different values. So the first one is the clearance of something called OF, and I just look at that table, and if you look at the first sentence, it says V is always going to be 5 mils per minute. All right. So I'm just going to put clearance of OF. I'm going to put UV over P. So the concentration off the table of OF is 250. It's in milligrams per deciliter, but it doesn't matter because it's going to cancel out. Times 5 mils per minute. Right. Divided by the plasma concentration, which is 10. Again, units are milligrams per deciliter. I'm not going to put them, it's going to cancel out. So 250 times 5 is 1250 divided by 10. So it equals 125 mils per minute. So if you just took these off the table, this is given. Put it in the formula, calculate it, 125 mils per minute. We'll come back to what that means next. Clearance of FNR, some substance called FNR. Again, off the table, the urine is 3 times 5 mils per minute. That's given again in that first sentence, divided by 0.5. So that's 15 divided by 0.5, that's 30 mLs per minute. Okay, so again, just calculate it. comes out to 30. The clearance of the last one, SBF, equals, the urine is given as 150 times 5 mils per minute again, divided by 4, 750, 187.5, I think, mils per minute. That's right. So, here are the different values that we got. So then we have to compare it to GFR, right? And figure certain things out. So the first one, the clearance is 125 mils per minute, which tells us the clearance is equal to GFR. So that tells us it's filtered, not reabsorbed, not secreted, right? Second one, clearance is greater than GFR, right? Sorry, less than GFR, which tells us it was filtered, but what? Reabsorbed. And in this one, clearance is greater than GFR, which tells us it was filtered and secreted. So if we're looking for one of these to measure GFR, which one will we use? OF, right? So not that you knew this, but OF was only filtered. That was mine for me. So clearance, FNR was filtered and reabsorbed. And then for the last one, secreted but filtered. So you should be able to figure those things out, okay? In terms of things, be able to calculate those and figure out what's going on. That was number 6. We got a number 7 too, very quickly. Bill has a whole bunch of urine, and what does that mean for Bill? Basically, he's got diabetes, but the key in this case is he's got diabetes mellitus like most people because he's got large amounts of glucose in his urine, right? And that's the big difference in terms of that. So basically, what is diabetes mellitus? What causes it? Diabetes mellitus is a disease where you either don't make insulin or don't respond to insulin, right? And that would mean you'd have a problem with your pancreas or potentially your insulin receptors in terms of your body. You would have high blood sugar. Because of the increased blood sugar, you can't reabsorb all of the protein. That's why we kind of bring up diabetes mellitus. You can't reabsorb all the sugar with your protein receptors in the proximal column tubule. Glucose spills over into the urine because you've exceeded transport maximum, and that's why Bill has a lot of urine. Okay? He could have had potentially diabetes insipidus. If he did, he wouldn't have high glucose amounts in his urine. It would be normal, right? But that's when you don't make or respond to ADH. If you didn't do that, the problem would be either in the kidney, on the principal cells where we respond to ADH, or where? Somewhere in the brain or the pituitary, the hypothalamus pituitary, which would affect how we produce ADH or how it responds to it in terms of that. Scientific terms, polyphagia, right, excessive eating, polyuria, excessive urination, polydipsia, excessive thirst, and again, we talked about why it exceeds, because you have exceeded the transport maximum. We've talked about that, enough, but remember, glucose appears in Bill's urine because he can't remove it all because it's high because he doesn't make insulin, so he can't put it in the cells. Make sense? That was a nutshell going through it, so we don't have to do it in lab. But we do have a few things to do in lab, but mostly just talk about your lab quiz, which shouldn't be too bad, and finish presentations today or tomorrow. All right? So make sure you're here so you get back your report and grade.
Two.